You did do better than us. This is dumb. I'm just sitting at the front of the room.
You got like 10 more seconds to get it out. I can't because my fourth period, you guys talk.
Oh my gosh, you're gonna make me roll. We're still playing chemistry. This is right now.
Alright, come back to me. Okay, come back to me. We'll chat some more, but I wanted to give you a little taste of like how a multiple choice question can be phrased with some of those. Because yeah, you've got to write your electron configurations out, and you've got to think about where the electrons are and think about subatomics. But we're gonna practice some more with that. Remember, quizzes are low stakes, right? They're minor portions of the grade in some respect compared to like a test. So that's why we want to see this in a different situation without our notes, so that you're able to do that. Okay. So before I move on from here, you guys actually wrote down some of the notes on trends yesterday from the part 2 of the interactive we were doing in our small groups. Everybody tell me, how does atomic radius trend? Meaning, I want you to tell me how it increases on a period and on a group. Yeah.
From left to right.
So it increases from left to right. Not this one. Are you doing this from memory?
Yeah.
Can you look at your notes? Look at your stuff you're going to say. Okay, so atomic radius does not increase from left to right. So it increases from
Top to bottom.
Okay, it does increase from top to bottom, and so I'm going to draw an arrow to say it increases from top to bottom. I'm going to put AR on it to put atomic radius. And how else does it increase on a period? Right to left, right? So if it wasn't left to right, guys, it had been right to left. We have no other option here. So right to left. So then on your little fake periodic table, draw just a sketch of one for yourself so you can work with this today. And it's going to increase from right to left. So as a reminder, the arrows are showing the which direction, increasing or decreasing direction. Arrows are showing increasing or decreasing direction. Increasing, right? Draw arrows in the increasing trend. Okay, yeah.
Aren't these most of the time?
These are most of the time. These are very general, right? We try to generalize things so we can work with that. It's hard to work with really specific information sometimes because it doesn't fit for everything. Okay, ionization energy. Who can raise their hand and tell me their stuff from yesterday, which way it trends? Grant. Half hand there. Ready? I don't remember. Yeah, I'm sure. Oh, 30 minutes. Okay. All right. Which way does it trend?
Increases as you go down in your.
Okay, so I'm gonna put some from down to up, but we mean bottom to top. Okay, down to up, and then what else? Right to left or left to right?
Right to left.
Left to right is what I heard from you. Okay, so it should be left to right. So basically, ionization energy increases up as you go up a group and across a period from left to right. So this is ionization energy. All right, everybody tell me electronegativity. How does it trend? The same as atomic radius or the same as ionization energy? Can you look back at your notes? Anybody? Yeah, Evan? Okay, or same as electronegativity is the same as ionization energy, right? And tell me about electron affinity, kinda. This was the roller coaster one, but you got a general trend. What is that one? Ionization energy or electron affinity or atomic radius? How does it trend? This was the fourth one on your stuff from yesterday. Left to right and bottom to top. Okay, so it matches the rest of these over here. Okay. All of those trend the same directions, meaning they increase going up a group and increase going across from left to right across a period. Here's how you're going to remember this. So I had to teach myself stupid things to remember this back in like 10th grade too. So do this with your fingers, okay? Doing this. All right, take your right hand and turn it to the left. Take your right hand like this. Right hand radius. Right hand radius. Atomic radius. Right hand radius. And then take your left hand and then flip it around. Make a little picture. Got a little picture? Take a picture up here on the table. Got it. All right, so you got it in your mind. Right hand represents the atomic radius, everything else is left hand. Right hand radius, everything else left hand. Right hand radius, everything in left hand. So what you will probably do on your test is you'll look around and be like, okay, and you'll draw it on your paper so you don't forget it. And that's why I've drawn it this way, so you cannot forget right hand radius, everything else left hand. So your fingertips are the arrows. That means that it's increasing in that direction. Okay, so now we're going to understand why this is the fact. Like, this is the answer. Let's figure out why this is the answer. Okay? And I'm only going to do maybe half the stuff today. I'll do the rest on Mondays. I'm going to give you some time to work in your groups. Okay? So take a second. This is the bread and butter. This is the guts of periodic trends. So this is the stuff I want you to write down first, and then I'll explain why this matters. So that skinny bit at the bottom. Well, I get this all word up. He's like cake apparently, because I'm cake person. I know you did. Here. All right, guys. So, can you next copy this down? Pretend that's right here. Good. Did you put that in the bag? Yeah. Okay. Just call me the excited state.
Pretty much.
Okay. Effective nuclear charge. We have a name for that to shorten that phrase down to something a little simpler, and that's called ZEF. Z-E-F-F. ZEF. Okay. The reason that's a shorter version of that is because the Z number is the like on the A to Z notation like this. What's the Z number? That's the atomic number, which is the number of protons. Number of protons, right? ZEF. Number of protons. Okay.
So that's like Jeff with a Z.
Yeah, so it's the cooler form of Jeff. This is L3O. Okay. So the nuclear effective charge is basically saying I'm an atom, and my specific atom is a specific size. But let's say I'm talking about an atom that's this big versus one that's this big. Okay, let me just give you an extreme example. And let's say I have, actually no, let me do another example. I didn't like that example. Let's say I have the same size atoms, okay? And let's say I have 12 protons in my nucleus versus 4 protons in my nucleus. Who has a stronger ZEF or nuclear effective charge?
12 protons.
The 12 protons, right? They are eager to hold on to their own electrons. So if there's electrons out here in the electron cloud, which there are, right? They're going to do a fantastic job of attracting because protons attract electrons. Whereas these 4 electrons that are hanging out here, the 4 protons, they don't have as strong of an attraction just simply because there's less of them, which is going to be called a lower ZEF or a lower effective nuclear charge. So one thing to think about though is when we add on energy levels, that actually makes our atom bigger and bigger and bigger and bigger. So we have to talk not only about the effective nuclear charge, but also this other factor called the shielding effect. So here's another example for this. If I am on a nucleus, people right here in the first energy level, we're really close to each other. I can keep tabs on what you're doing. Okay, we're close enough to each other where you are on lockdown. But then wave your hand from here in the valence shell. Okay, you guys are the crazy, like outlandish children who I can't really keep an eye on and keep tethered to me. So you're super reactive, and there's not just, I mean, we don't think that, okay, yeah, that makes sense. There's a reason for that. All these electrons on this row, and this row, and the third row, they're in the way of my positive attraction, so to Grant's negative attraction, okay? So you guys are all in the way. So what are you doing from the perspective of the neutron, the nucleus? My positive charge can't get to that negative charge because you guys are in the way, so you guys are doing what? Dampening that, which we can call shielding that, right? So you guys are shielding the positive attraction to the negative electron so that it doesn't have as much of a pull back into the nucleus. So the shielding effect is caused by electrons in the inside, so like the inner core electrons. They're blocking the positive pull of the nucleus to the outsides. So how does that look? We have this proton nucleus thing in the middle, and we've got these electrons outside, and we've got this proton set in the middle with whatever number it is. And let's say I've got 1, 2, 3 energy levels. I'm going to put 2 in here. So the protons, can they more effectively attract to this scenario or this scenario? Can they more appropriately attract their electrons?
Neither, because there's no shielding.
Well, there's electrons inside of these inner core. Okay, this has how many energy levels?
1.
Let's just call this the nucleus, okay? So 2. So there's 2 energy levels. Okay, how about here? That's the nucleus. 1, 2, 3. 3 energy levels. Energy levels. So the protons and the electrons in the valence shell are closer together than in this situation. So who would have more shielding going on? 3, because there's more layers of it's like an onion, right? Think Shrek. You gotta go way down to get the good stuff. But you've got all these layers in the middle that are blocking the attraction. Okay? It's just a good memory. Okay. So what we're gonna mention are 2 things. Whenever we talk about this out loud, we have to mention the effective nuclear charge, and we have to mention the shielding effect. So this up here, I'm going to make it big and broad here. This is a period trend. So when we're talking going across the period from left to right or right to left, and you're mentioning 2 things there, you must mention the effective nuclear charge. If you're talking about 2 things on the same group, then you're going to mention the shielding effect. So this is a group reasoning that will go along with our trend discussion. This will make more sense once we apply this, okay? All right, so we got that. So the atomic radius. We've already mentioned the fact that it increases which way? This. What is this?
It's top to bottom.
Okay, so it increases from top to bottom and left or right to left. So we know that's the general increasing nature of it. But we can also speak of it from the decreasing nature of it, which is why some of this might be a little opposite. So as we go across the period, I'm going to give you 2 examples as we go. So let's do lithium, and I'm actually going to do that down here. Lithium, and who's all the way across the period from lithium?
4.
Let's keep going.
Sodium.
Who's F?
Chlorine.
Fluorine. Okay. So write down the examples with me as we go, okay? Yours are only a little more easy. So lithium has how many protons in it? 3 protons. Okay? And fluorine has how many protons? 9 protons. Okay. As if we were drawing electron configurations or writing them out, you would say that you went through all the way to get to lithium. You've gone through 1s2, right? And then 2s2. So what does that 2 in the front mean about its number of energy levels it has? 2, right? So I'm going to draw that as the first energy level. I'll draw this as the second energy level. Okay? Fluorine, same story, right? 1s2, 2s2, but 2p6. It doesn't matter if it's 2p6. It just is the fact that we still are in the second energy level. They have 2 energy shells just like this one does. So far they kind of look the same, but here's the big deal. This one having 3 protons versus this one having 9 protons, there's a big difference in how well they attract their energy shells or how well they attract their electron cloud. Who attracts their electron cloud better? 3 protons or 9?
Chlorine.
9. Okay, so the 9 protons are like, come here electron, scooch in here. It's like an attraction, so it pulls the electron cloud in. So it causes it to shrink some, right? So this one's smaller, and this one is larger. So how does the atomic radius trend? Increasing which way? From right to left. This one's smaller, and this one's larger, and let's talk about why. So the reason lithium is larger is because it has a lower ZEF, nuclear effective charge. This one has a higher ZEF, or nuclear effective charge. And how am I determining its nuclear effective charge? I'm simply looking at what? The number of protons, right? You just wrote down a nuclear effective charge. It's all about the number of protons. So that allows us to then see the trends. So basically, I already told you the answers. This is the trends, guys. We got it. But this is the reasoning behind it. Okay? So I gave the example of across a period. I think we were on n equals 2. We were on the second period. Let's go down in lithium's group. Who's at the bottom of lithium's group? Who? Francium? Okay. So I'm kind of going in order here. So this is the second group. I'm going to kind of go down to francium. So how many protons does francium have? 87? All right. How many energy levels does francium have? Energy levels. 7, you say? 1, 2, 3, 4, 5, 6, 7. I can't make this any more obvious. Why? Why in the heck? Why is francium naturally bigger than lithium? Because it has more energy levels within its electron cloud. It has nothing to do with the protons. Okay, so we mentioned protons looking across a period, which is why we mentioned ZEF. Going down a group, we're not talking about protons, we're talking about energy levels. And with that energy level idea, you're going to be able to tell me now, can francium even see this electron that's way out here?
No.
It doesn't even know it's there, right? That's a valence electron that's shielded by 6 energy levels worth of electrons in the middle of it. And it's like, heck yeah, you can go do what you want to, honey. I don't even need you in my little shell anymore because I can't even attract that valence electrons. It's so far away. It's really easy to attract electrons that are right next to you, but less so in the opposite situation. So what we would call this is it's bigger. It's bigger because it's got more energy levels, and you can mention the electron shielding.
Would it be more reactive to?
Yes, super reactive. This would be really reactive because it doesn't have any kind of lockdown by mama nucleus. Yeah.
So if we're comparing like 2 of them in the same period, the ones on the left would be bigger?
If you're across the period, the ones on the left are bigger. And if you're going down a group, the bottom is biggest. So on the periodic table as a whole, let's say as a whole, who's the biggest atom on the periodic table? Francium. Who's the smallest atom on the periodic table?
Helium.
Supposedly helium. Sometimes we ignore the noble gases because they kind of have an interesting play. Like I would say like fluorine or helium would be pretty small. Okay? Question, Izzy? Okay, we're going to do some more examples which will help you get there. Okay? So quick review here. We went with the atomic radius. We went with the atomic radius. Guys in the back, hush. Thank you. With the atomic radius, we looked across a period. When we look across a period, we're worried about nuclear effective charge, which means we have to count what? Protons. 3 protons versus 9 protons. Who pulls on their electron cloud better? 9 electrons versus 3, just because that by the nature of more positives means it can attract its electrons better. It shrinks the the electron cloud, which makes it small. So comparatively, who is bigger, lithium or fluorine? Lithium, which follows our trend, our atomic radius trend. That side's bigger. And then, as a second situation, we look down a group. And this is just if I'm saying, who's bigger, lithium or francium? You have to rationalize why francium is bigger. Don't just say, oh, it's the lowest in the group, because I know you're just telling me with your finger trick here. I want to know why. It's because it has more energy levels with electrons in them, and those energy levels cause electron shielding. So the two factors you're always going to mention are what and what? Nuclear effective charge and the shielding effect. Okay. Let's do this one actually kind of adds on to this. We're going to talk about I already did that. We're going to talk about ions before I move on to the other stuff, okay? So let's think about an ion and why it possibly could change the size or shape. So if I have lithium, let's draw our lithium again. How many protons does it have? 3 protons, okay? Let's call this its first energy level. And I'm going to draw it like you guys used to for now. There's its second energy level. So it has 1, 2 electrons. So that's like 1s2, right? And then what do I add on the outside? 1 electron for its 2s1, okay? Lithium's in group 1. How many valence electrons does it have?
1.
It has 1 valence electron. Is it going to gain 7 electrons or lose 1? If it were to form an ion, yes, it would lose 1. Guess which one that would be? Which electron would that be? The valence shell, right? The 2s1 would be gone. So basically, as it loses 1 electron, it's going to form a cation. And as it does that, it's now going to be like lithium, but still with its 3 protons, but just this first shell. Just that first energy level. So is this one bigger, or is this one bigger?
The first one.
First one's bigger, right? So in the atomic phase, like just as a neutral atom, it's bigger than when it forms its cation. And that's because cations always lose their valence shell. So by the loss of an energy level, it gets smaller. Okay, so the atomic radius of a cation is smaller than its, kind of like we call it the parent atom. So why is the cation smaller? Evan.
Because it has less energy levels.
Okay, perfect. You have a question?
Yeah, and the parent atom is the same as like
The original that it came from.
neutral ion technically.
The neutral atom, yep. All right, similar situation. Yeah, question?
I was going to ask a question.
Let me go through the situation first, okay? Let's do fluorine, because that was the example we used earlier. Austin, do you have a question? Okay. So fluorine has how many protons? 9 protons, and it has 1s2, 2s what?
2.
So this is 1s2, 2s2, 2p5, okay? I'm just doing the second energy level all together just for clarity. There's 2, 4, 6, 7, okay? So there's 7 valence electrons here. Is it going to gain 1 or lose 7 to get to octet? Gain 1. So as this gains 1 electron to form an anion, I'm going to actually draw it on top of this picture just for easiness sake. 1 extra electron pops in here, right? So I'm just going to add it right here. Big and bad, an electron. Well, what is this electron naturally going to do sitting next to this electron and this electron?
Push them away.
Right, they repel. Electrons do not like to be next to other electrons. They're negative, negative, negative. So think about this. Okay, hold up your hand like this. This is your valence shell with your 7 electrons, and you added another electron, and they repel. What do you think is going to happen?
That's nice thing.
Yeah, they just repel. They just push away. So this one's bigger. So the anion is bigger than its parent. The cation is smaller than its parent, just by the nature of how the electrons are lost or gained within the shell.
But would a cation be like smaller, like in proportion to an anion being bigger?
Yes, but sometimes it differs based on how big they were to begin with. That's why we have to kind of know the general rules first. All right, give me a thumbs up if I can move on from here. Okay. I'm going to go over one more just for the trend purposes, and then I'll stop. Okay. So ionization energy, you can just label it IE. The definition of this was in your reading guide. So do you recognize this? I sure hope so, right? Or maybe you just make an extra note on reading guide. But what does VE stand for again? Valence electron, right? All right, so IE. ionization energy. Energy needed to make an ion. So that's why it should kind of make sense with the name of it. Energy needed to make an ion. It's not just any ion though. It's the cation version. Let's do our logic game first. So write down your little 2 sentences here and then we'll fill in those blanks, okay? All right, so thinking about the first sentence here. It's going to take less energy to remove an electron far or close to the nucleus? Far from the nucleus, right? So far from the nucleus, less energy to remove an electron that's far from the nucleus. So for example, that's like a valence electron way out here versus one that's really close to nucleus. So I'm on a nucleus. Who would be the farthest, or who would be the electrons that are most difficult to get away from me? You guys up here, right? You guys would be like, peace, I'll see you later. I really can't control the fact that you guys are that far away, but I wouldn't be able to attract you guys that are farthest away from me very well. So it's really easy to get this electron. It's really hard to ionize or take that electron away. So it'd be easy to take that one, it'd be hard to take that one. Okay. Yeah, the closer you are to the nucleus, the more attracted you are to the protons. So basically you guys are telling me that it is easy to take electrons from big or small atoms. From big or small atoms. Thank you. Big or small atoms. What's next? Big or small atoms. It's easier to take from big atoms, okay? Okay, and it's harder to take electrons from small atoms. Okay, do you see how that's an inverse relationship?
Yeah.
Not a lot of energy for big atoms. So small amount of energy is required for big atoms. A lot of energy is required if you're going to take it from a small atom. Okay, so you remember your right-hand radius, right? Right-hand radius, where's the biggest one?
On the left.
So on the left and the bottom, right? So the left bottom area. So francium. And then what did the other hand stand for? Everything else. Okay, that's cheap. But ionization energy is how we can say that along with the others. So that's why they go in opposite directions. Because the big atoms versus the small atoms, this one's going to require very, very little energy to take an electron. Okay? And these are going to require a lot of energy to take an electron. And that's the ionization energy. Ionization energy runs the opposite direction of atomic radius. Yeah. Because it's labeled as decreases. And I tried to stop doing that. So if I always give you the finger trick and you say, okay, increasing nature of my fingertips, you'll always remember it. But you can imagine you can explain it in 5 different ways. Okay? This works the best for you guys. All right, so really quickly, tell me why this works. What is the trend or the factor you have to mention if you're going across a period? I heard it. Somebody louder.
Effective nuclear charge.
Okay, effective nuclear charge. So over here, I'm going to draw this in red. Over here, these atoms are larger than these, right? Just because of the nature of the atomic radius. So who has a more effective nuclear charge?
No, large.
1 or 2? Who's better at pulling their electron cloud in? 2. All right, so you guys are telling me the effective nuclear charge increases from left to right. So this one, not a really good strong electron, hold on to electrons. This one, super strong hold on to electrons. So as the effective nuclear charge increases, it gets harder and harder and harder to take the electrons, meaning the ionization energy is increasing. Okay, going down. This one's smallish compared to this one, right? So who has a higher ionization energy? 1 or 3? 1, because it's, don't say it's smaller.
It has less.
Less, what's the factor we talk about on a group?
Ionization.
Zeph, nuclear effective charge was the one factor. Say it.
Shielding.
Shielding, right. So it has less shielding. Therefore, the nucleus is like, whoa, these are my electrons, you can't take them. Whereas down here, the nucleus is like, what? I got electrons out there, you can have them. Because it doesn't really know necessarily there's electrons that far off because they're so far away. So it'd be really hard to take an electron from this atom, but it'd be pretty easy to take an electron from this atom. Okay? Alright, so let me stop there, because I can do the rest of this on Monday. So, problem set 6, you saw the chart? Some of that stuff, this will help you figure out pieces that when you're ordering them, but I need to do some practice with you as well. So try to tackle a little bit more of that, but know that we'll talk Monday for questions that you specifically have. Okay? Yeah.
Yes.
I want to see some progress, but I'm not going to take it on Monday. Okay? So what I want you guys to do now, I left you about 30 minutes. You have group work time for your atomic model problem. If you need any assistance, please let me know. Be productive. Be productive.